हमको रीड आ गई है हाँ हाँ मेरे रीड आ गई है काम रीड एक मिनट है
like this confusion. This projector is too much out of
चल रहा है ठीक है
yeah, one is enough.
जरूरत नहीं
Can introduce now. No? So, good afternoon, everyone. Welcome to the speaker for today's seminar. Today we have Professor Gregg A. Wade from the Department of Physics and Space Science, Royal Military College of Canada. So he will speak about magnetic fields, convection, pulsation, and the chemical peculiarities of cool A-type stars. Okay, so let me introduce Dr. Wade. He investigates the structure, evolution, origin, and impact of magnetic field in stars. His research concentrates on intermediate and high mass stars, where he investigates the role of magnetic field in generating spectroscopic activity and in mediating accretion in late stellar formative stages. So Dr. Wade is the PI of the magnetism in massive star collaboration. He is also co-PI of binarity and magnetic interactions in star project. Okay, so he is also recipient of Royal Military College Cowan Prize for excellence in research in 2019. So, yeah, Professor Gregg, yeah, we can start.
Thank you very much. Thanks for coming out today, folks. We appreciate you being here. Thanks to Santosh for arranging this seminar. And thanks very much to Aries in general for the very warm welcome that Eugene and I have received since we finished the conference in Dintao and have spent the last few days here. Can everyone hear me okay? You raise your hand if you work in a field related to stellar astrophysics. Okay, so a few people. All right, but most of the other people look like they should have enough experience that they'll know generally what I'm talking about. Okay, so today I'm going to talk about the coolest stars that reside on the radiative side of the convective boundary on the HR diagram. So stars with radiative envelopes, but still with interesting properties, in particular the host magnetic fields, and as a consequence, have strong chemical peculiarities and pulsate and generate a variety of phenomena that help us to understand and provide insights into the characteristics of stars below the surface. So I'm an expert in stellar magnetism, and so this is principally a talk about the magnetic fields of stars, notwithstanding the title. It's also a new talk because Santosh said, no, I don't want you to give that talk, I want you to give this talk. And so I only just finished it about 3 hours ago. I have no idea whether it's 45 minutes or an hour and 45 minutes, so we're going to see what happens. So you'll recognize this as an HR diagram with luminosity along the vertical axis effective temperature along the horizontal axis. Each of the black dots here is a star that was observed as part of the Hipparchus mission. And you can see that the diagram is divided into a number of colorful sectors that correspond to the general bulk internal structure of stars that reside there. So stars down here on the right-hand side of the diagram are M dwarfs. These M dwarf stars are fully convective. They have no radiative or convective core. They convect through the surface all the way down to their interiors. Stars in this green or yellow region have structure like the sun. They have an exterior convective envelope that resides on top of a radiative zone below which the nuclear reactions take place. And then finally, the stars that I'm particularly interested in reside in this white area. And those are stars that have radiative envelopes and convective cores. And what's very interesting is that the characteristics of stellar magnetism trace the bulk structure of stars across this diagram. Now, there aren't going to be a lot of equations in this talk, so don't be afraid, but it is useful to see the connection between the physics of stars and the basic fundamental physics that allows us to understand the evolution properties of the magnetic field. So this is the so-called dynamo equation, or the induction equation, and it tells us about how magnetic fields change and evolve with time as a function of an existing magnetic field and different velocity fields. So in this particular equation, the first term is normally interpreted to correspond to stellar rotation or differential rotation. And this is the omega term that appears in the terminology of the solar dynamo, the alpha omega dynamo. The second term corresponds to convection or turbulence. And the reason that we think the sun has an alpha omega dynamo is because both of these quantities, both of these physical mechanisms are relatively important in driving the characteristics of that dynamo and generating the sun's complex and variable magnetic field. And you can see that both of those terms have positive signs in front of them. So they contribute in a constructive way to dV by dt. And probably all of this makes sense because you've all taken introductory courses in electromagnetism and maybe even stellar magnetism. But this third term is one that people usually aren't familiar with. This is a resistive decay term, and you can tell because it's got a negative sign in front of it. And that's because stars aren't perfectly conductive. They have a non-zero resistivity. And that means that if you drive a current in a star and you don't maintain that current through some positive process, that current will eventually decay. And I'm very interested in this last term because it corresponds to the basic physics of magnetic fields in stars in the white region of the diagram that I showed you. So we can illustrate this by assuming a star that has no rotation and no convection taking place, just like, say, an A or a B or an O star on the main sequence. And if we do that, we can do a little bit of mathematical magic, and we can demonstrate that this third term here, which has this kind of inscrutable structure in the original equation, is actually a diffusion equation. So you've all done partial differential equations. If you take a differential equation that corresponds to a diffusion function, you're going to extract a solution to that equation that provides a characteristic diffusion timescale. And equation, that diffusion timescale looks like this. So it has a term on the top that corresponds to the diffusion length, which is basically the size of the star. And the second term on the bottom here is called the magnetic diffusivity. And it's a function of the conductivity of the star. So if you think about a typical star, something like the sun, it's big, right? It has a very large value of L, and it's also highly conductive. So that means that this term here is relatively small. And so that means that this value of tau, this characteristic diffusion time, is quite long. In fact, if you calculate it, it turns out to be roughly the same as the sun's time on the main sequence, about 10 billion years. And so what that tells us is that if I implant a magnetic field in a star, even if I have no rotation or convection in order to support it, that magnetic field will take a long time to go away. And so that leads us to the two basic kinds of magnetism that we believe exist on the HR diagram. The first you're totally familiar with. They're called dynamos, right? So we're taking mechanical energy from rotation and from convection, turning that into electromagnetic energy in a cyclical way. But what you're probably not familiar with are the magnetic fields that exist up here, where there's no convection taking place, or relatively little convection taking place, and yet magnetic fields still exist. And we call those fossil fields. These are the remnants of magnetic fields that were generated earlier in the star's evolution and now have no positive mechanism to sustain them, and so they're slowly decaying with time. But that decay is very slow on account of the time scale that we've just calculated. And these are the stars that I'm particularly interested in. So the focus of the talk today is going to be on this particular region right here, this orange line that separates the white region from the yellow or green region. This is the so-called convective boundary. This is where theoretically the hydrogen convection zone that we see in the solar granulation disappears as we move to higher temperatures. And I'm going to be focusing specifically on stars that reside here, just to the left of that convective boundary, and looking at their characteristics as we move close to a convectively dominated state. Now, I want to give you a little bit of a feeling for how we know that that convective boundary that's predicted theoretically actually exists. But before I do that, I'm going to introduce you to this particular Kippenhahn diagram. So this is a diagram that shows the internal structure of stars. This is the center of a star. This is its surface. These are stars of different masses. So this is a star with the mass of the sun. These are massive stars over here. The white regions are radiative and the fluffy regions are convective. So you can see, for example, that if I think about a star like the sun, it has a radiative interior and then it has a deep hydrogen convection zone. So the stars I want to focus on, and just before I do that, I'll point out that this is a broken diagram, right? It's not the scale. We're only going down 3% here, and then we're going down 20% here. There's a huge piece of the star that we're not seeing here. So this is what I like to focus on. This is the region on the main sequence between about 8,000 Kelvin and about 6,500 Kelvin. So a little bit hotter than the sun to stars that are of mid-A type. And this is where I'm going to be focusing because I think it's very interesting that in that region, we go from having very superficial convection in stars with temperatures near 8,000 Kelvin to very deep convection for stars that have temperatures closer to 6,500 Kelvin. And these are all stars in which the kinds of characteristics that I'll be speaking about tend to occur. Okay, so let's talk about this transition region and what we see there. So there are three key transitions that we observe at the convective boundary. The first is called the granulation transition. Granulation is, of course, the tops of the smallest convective cells that we can see at the surface of the sun, and they correspond to fountains of material, hot material that's coming up and then raining down as it releases its heat on the outside. And we can diagnose the existence of granulation in stars, even if we can't resolve their surfaces, by studying their so-called line bisectors. And line bisectors are really easy to understand. This is a spectral absorption line. To create a bisector, I draw a straight line across. I do this at different depths within the line, and then I connect them through their centroids. And in this particular case, this is the magnified bisector. And you can see it's not straight. And that's because this spectral line, if you look carefully, is slightly leaning toward the right. And this is exactly what we see in the case of the sun. We see bisectors that lean to the right because the upflows of material in the sun are hot and the downflows of material in the sun are cool. They're slightly Doppler shifted relative to one another because of their relative motions, and because the downflows are less bright, that causes this depression of the blue wing. And so if we look at stars on the right side of the convective boundary, like the sun, they all have bisectors that lean slightly to the right, as you'd expect from solar light convection. But if you start looking more and more to the left of the convective boundary, you start seeing bisectors that lean to the left. Now, the specific physics of these particular bisectors isn't something I'm going to go into today, but the important point is that they diagnose a difference in the convective properties of stars as you cross that boundary. So this was studied by David Gregg and his student Thomas Nagel in 1989. They created this diagram. This actually shows stars going from the main sequence up to supergiants as a function of spectral type. These different symbols denote stars that have right leaning, like this, bisectors, and these ones are left leaning bisectors. And you can see that at hotter spectral types, we have left leaning bisectors versus right. And they were able to determine what they called the granulation boundary that separates these two. And you'll notice that at the main sequence, this corresponds to a spectral type of F0, or about a temperature of about 7,000 Kelvin. So the first piece of evidence that something is physically happening is from the bisectors of stars and the presence or change in granulation. The second transition relates to chromospheric activity. So what I'm showing here, and I'm sorry that it's a little bit small, this is the core of the calcium 2K line in the sun, shown in two different states. One is for the quiet sun, and the other is for a plage region where the magnetic field is relatively intense. And what you'll notice is that there's strong emission in the core of this absorption line that diagnoses the presence of a chromosphere around the sun. We know that the sun has a chromosphere. But you can do the same thing, of course, with other stars. So you can find stars like 36 Ophiuchi here that have very strong chromospheric emission, a very strongly active star. Other stars that have much weaker chromospheric emission. And so we can study this in stars across the convective boundary, and we come to a conclusion that stars that live on the right-hand side of the convective boundary tend to have relatively clear chromospheric emission, while most of the stars that live over here have no chromospheric emission. If we believe that the chromosphere is a consequence of the sun's dynamo magnetic field, then that's also telling us that the convection which helps to power that magnetic field is changing in a significant way across that boundary. The third transition, and probably the most stark, is related to rotation. So this is a diagram from a paper from 1967, and honestly, I think it's the best illustration of this phenomenon. It's a little bit busy. You can ignore the dark circles down here. What we're looking at here is an HR diagram. This is the zero-age main sequence. You can see evolutionary tracks going from one solar mass up to 1.4 solar masses. And the individual stars are coded according to their projected rotational velocity, how quickly they're rotating. And you can see that somewhere about here, the stars that are really rapidly rotating start to disappear, and the diagram begins to be dominated by stars that are quite slowly rotating. And this is a phenomenon related to magnetic braking. So we know that the sun rotates once in about a month, but it didn't originally rotate at that rate. It's spun down because of angular momentum loss, mitigated through its wind and magnetic field. And so it's, again, another indication of the solar-like dynamo that provides an ability for stars to break on one side of the convective boundary and the lack of such an ability on the other side. It's even more stark if you look at this diagram again from one of David Gray's papers. This is projected rotational velocity, again, as a function of spectral type. And you can see that around a spectral type of F8 or so, the rapidly rotating stars utterly disappear. Okay? So something really fundamental is happening on that boundary, and it behooves us to study it in so much as we want to understand the physics of stars and convection. Okay, so we're going to come back to this diagram, and I'm moving around now, so my core temperature is going up. Pretty soon I'm going to have to unzip. So we talked about the existence of dynamos and fossil fields, and this is our boundary here. So what I'd like to do now is talk about the stars that reside just to the left-hand side of the orange line here. So these are stars with fossil magnetic fields, and I'm really glad to see my little movie is working here. That's nice to see. So we find fossil magnetic fields in about 1 in 10 stars that have radiative envelopes. So 1 in 10 A, B, and O type stars, and a few F type stars as well. These magnetic fields are organized. They have topologies that are approximately oblique dipoles. The strengths are very strong. They range from about 100 Gauss to more than 10,000 Gauss. So think about a sunspot, but with that strength of magnetic field distributed more or less uniformly over the surface of the entire star. Of course, the star doesn't look dark because they don't convex, so there's no convection to suppress. What's very interesting about these magnetic fields is that they don't correlate with rotation. They show no systematic change with mass. So all of the things that we see in the case of dynamo-generated magnetic fields on the lower main sequence don't seem to apply to these magnetic fields. They are fundamentally and qualitatively different from dynamo-generated fields. Moreover, they're very stable, but you knew they would be, right? Because we know the diffusion time scale is so long, we don't expect to see any changes in these magnetic fields. And then many of the stars that host these fields are very slow rotators, but some aren't. And that's probably not something we'll talk about too much today, but if you're curious about it, we can talk about it afterwards. And of course, what I was showing you here is a numerical model that seeks to illustrate the structure of a fossil magnetic field in a rotating star. So you can see that there are two magnetic poles. There's a positive pole and a negative pole. And that magnetic field isn't aligned with the rotation axis, but rather it's tilted relative to the axis. Okay. So now I'm going to focus on the specific stars that lie just to the left of that convective boundary, stars that we call AP stars, and in particular the coolest of the AP stars. Okay, so AP stars are, by virtue of their classification, magnetic stars. They have radiative envelopes, so they're not yet convective. In this definition, they're going to have temperatures between about 6,500 and 8,000 Kelvin. This is entirely arbitrary. This is about the temperature of the coolest of them. They're quite rare. Only about 1 or 2 in 100 F-type stars are cool AP stars. And the magnetic fields in these stars, because they're non-convective, have to be fossil fields. Okay, so how do we know that these stars are magnetic? So this is a figure I've taken from a very recent paper by Gauthier Matisse and his collaborators, focused on a particularly interesting cool AP star that they were studying. And there are two pieces of fundamental information in this figure that tell us that the star is unequivocally magnetic. The first is the star has strong circular polarization. So this is Stokes V down here. And you'll notice that in each one of the spectral lines, there's a little wiggle of circular polarization. That's due to the Zeeman effect. I'm not going to go into the details today, but again, if you're interested to ask me afterwards, I'm happy to tell you a little bit about it. But something that you'll be more familiar with is the fact that this particular star, if you look carefully at this spectral line right here, is split into two components. This is the classical Zeeman splitting that results from an atom in a magnetic field. This happens to be an ionized iron line. And this particular splitting can be measured to diagnose a magnetic field strength of a little under 4 kilogauss. So this star isn't alone. There are many cool AP stars that show magnetic splitting in that line, as well as other spectral lines due to strong magnetic fields. So magnetic fields like this are very common, in fact, probably ubiquitous in all of the coolest AP stars. And the great thing about this sort of diagnostic, and we were talking about this earlier, is that it's really easy to interpret. If we compare a magnetic star with magnetic splitting to a non-magnetic star, we can identify the same spectral lines. We can easily calculate the Zeeman pattern associated with each one of these lines. And based on the Zeeman pattern, we can easily compute the modulus of the surface magnetic field of the star. Okay, so we've talked about their magnetic fields. Let's talk about their distinctive chemical peculiarities. So the P in AP is a spectral classification index that tells you that the spectrum is peculiar. Doesn't really tell you how, but it tells you that there's something funny in it. And in this particular case, it means that the spectrum is typically rich in iron and chromium lines and lines of rare earth elements like neodymium and yttrium and praseodymium, elements that we don't usually think about. These enrichments in chemical elements are a consequence of slow diffusive accumulation of these atoms from the interior of the star under the competing effects of gravitational settling and radiative levitation. And I'll show you a little bit about that in a second. But the point is that this is only a superficial effect. These stars aren't chemically peculiar in their centers. They're only chemically peculiar in specific regions in their atmospheres, the parts of the star that we can see. This diagram shows the chemical abundance distribution derived for this particular cool AP star by Geldman in 2000. What's shown here is the abundance on some scale that you probably don't need to care about, except that it's logarithmic. And this is atomic number here, going from 0 to 80. The black dots correspond to the star. The open circles correspond to the sun. And so there are three takeaways from this diagram. The first is that cool AP stars tend to be underabundant in light elements, carbon, nitrogen, oxygen, helium. You tend not to see them in the atmosphere because they settle. These stars tend to be slightly overabundant in iron peak elements, say a factor of 10 to a factor of 100. But where these stars really shine is their extreme overabundance in rare earth elements. You can see that the gap here is huge. In this case, it's about a factor of 10 to the 4, but in some of these stars, the apparent enhancement can be up to a factor of 10 to the 6 in the atmosphere. You're probably noting something kind of fundamental about this process. Elements that are relatively common in stars that have high abundance tend to have relatively little difference in abundance relative to the sun. And elements that are very rare, that correspond to perhaps 1 in 10 to the 9 atoms in the atmosphere, can be enhanced significantly. And there's a reason for that. I'm not going to describe it now, but again, if you have a question, I can answer it at the end. So another reason that one of the reasons that we know that this is an atomic physics effect rather than say an effect related to the formation of the stars and peculiar abundances in the region of formation is that if we study abundances of, in this case, chromium and iron as a function of effective temperature in samples of stars, we can see that those abundances change in a systematic way with effective temperature. And that's telling us that the thermodynamic conditions in the atmosphere are what's driving the change in the abundance table of individual stars. Okay, so these stars have extremely chemically peculiar atmospheres. But what's even more stunning is those chemical peculiarities are isolated in particular regions of the star's surface. In other words, the surface is spotty or patchy, but it's not patchy in brightness or darkness. It's patchy in accumulation of chemical elements. And we can show that by using a method called Doppler imaging, where we take a rotationally broadened spectral line, and as the star turns, we can study the modulations of that spectral line due to features on its surface. And so by taking time series of spectral lines, so these are all lines of, I guess I don't need to reach, do I? These are all lines of iron, chromium, and silicon here as a function of time for a particular star. And you can see they're all changing with time. There are bumps and wiggles that tell us about the structure of the star visible at that particular time. And then by obtaining an observation at a successive time, the star is turned slightly, and we can see a different part of the star. So using this information, we can tomographically reconstruct the star's surface, and we get something a little bit like this. So this is for the cool AP star HD 24712. At the top here is the star's magnetic field. Again, there are 5 rotation phases, so you can think about the star rotating from here to here to here to here to here. The vectors of that magnetic field are shown along here. And then down here are the chemical abundances of different chemical elements. There's magnesium here, there's scandium, titanium. But in this particular paper by Teresa Luftinger in 2018, she did about 15 other elements. I just don't have enough slides for that. Okay? But what I do want you to notice is that each one of these chemical abundance distributions has a contrast. And that contrast is typically some part of a factor of 10 or around a factor of 10. And you'll notice that the abundance distributions of different elements, for example, compare cobalt to iron, can be quite different. And again, that's diagnostic of the different ways that different atoms or ions diffuse within the magnetized atmosphere of the star. So this is all understood within the context of microscopic diffusion within the atmosphere of the star, radiative levitation, gravitational settling. Most of this actually came out of the PhD thesis of Georges Michaud back in 1970. Georges predicted basically all of the phenomena that we see, that some elements should be underabundant, that some elements should be overabundant, and that the magnetic field should provide a way of breaking the symmetry of the stellar atmosphere and generating patches on the surface. So
diffusive properties are same for all the elements, or they depend on the charge?
No, they depend very much on the element. So on the excitation potential, on the ionization potential.
And then you get the patches on the surface. So they also depend on these kind of diffusive properties?
So empirically, they must, but that's a harder problem to solve. I haven't referenced any of the more recent work that's been done in order to try and solve that problem, but it's unsolved and there's current work taking place. Yeah, good question. I'm just going to skip over these next 2 figures. What I was going to say is that there's some really strong evidence that this is actually taking place and that these accumulation layers in the atmosphere really exist. Again, if you're curious to know about those, I can tell you about them at the end. Okay, so the last point I'd like to make in talking about cool AP stars is that some of these stars are non-radial pulsators. And of course, that's a specific interest here at Aries. Santosh has been leading a group working on this particular problem for a long time. These particular stars are important to astroseismology, allowing us to sound the interiors of stars and improve our theory of stellar evolution. So the first rapidly oscillating AP star, as they're known, was discovered in 2000 by Kurtz and Martinez. And what I'm showing here is brightness as a function of time, folded here and here and here. If you look carefully, this is in hours, right? So this is going for 2 hours. You can see that there are many pulsations taking place here. So these are literally rapid pulsations. The time scale of these pulsations is typically between 5 and 15 minutes. So these are high overtone acoustic P-mode oscillations. They're low order, so they're typically dipoles or quadrupoles. So you can think about the star kind of squishing one end and then alternately squishing the other end. And they're aligned with the magnetic field of the star. Okay, so they're magnetoacoustic waves. Here are some modern observations of an roAp star. These are test observations from Holdsworth 21. What I'm showing here is not the pulsation light curve of the star, but rather the rotational light curve of the star. So this is phased according to the 6.7-day rotational period of this particular object. And we see a variation on the rotational period because the different patches of chemical elements redistribute light to different regions of the spectrum. And so the optical flux of the star actually is modified by the presence of those patches. And so as the star rotates, we also see luminosity or magnitude variability. Down here, this is the Fourier amplitude spectrum related to the pulsation. So here's the central peak in the Fourier amplitude spectrum. So this frequency corresponds to a period of 14 minutes. And what you'll notice here is that instead of there being a single peak, there are 3. And this is rotational splitting. So it's the coupling between this pulsation and the rotational period on a time scale of close to 7 days. And that's because, as I mentioned, these particular stars are magnetoacoustic pulsators. The magnetic field and the pulsation axis are aligned with one another. And that means that as the star rotates around its rotation axis with its magnetic axis or pulsation axis tilted, there's a modulation of the pulsation light curve with the rotation of the star. And so they're intrinsically coupled, hence we see 3 peaks in the Fourier amplitude spectrum. Okay, so that's my introduction to the cool AP stars. I want to come back to this boundary again. And in particular, I want to talk to you about a study that we've begun to undertake. It's been running for 2 years now, but mainly my students have been focused on it. I've been doing a lot of administration for those 2 years. And I'll give you a flavor for the kind of physical questions that we're asking about stars that live near this boundary. Okay, so I'm actually going to talk to you about a 4th transition, right? I talked about 3 before. I talked about the granulation boundary or the granulation transition, the chromospheric activity transition, and the rotational transition. But there's another one that most people don't talk about, and that's the fossil field transition. The fact that fossil fields disappear when you pass that boundary. And to illustrate that, here's an HR diagram. This is from the PhD thesis of James Sikora back in 2019. So again, this is luminosity, this is effective temperature. So these are evolutionary tracks from about 1.5 to 3.5 solar masses. And there are 2 sets of symbols here. The blue symbols are all of the known magnetic AP stars within a volume of 100 parsecs centered on the sun. So this is a volume limited sample. This is extracted from the Hipparchus catalog. Yes, we could do it with Gaia nowadays, but you couldn't at the time. The gray symbols in the background are all of the other stars in that same volume. Okay? So we're able to take 2 samples, one the magnetic star sample, the other the non-magnetic star sample, and compare the 2. If you look carefully, it kind of looks like there are roughly the same number of stars, same number of blue points at most masses across this diagram. You might notice there are slightly fewer down here, but it's not a big difference. But if you look carefully at the gray points in the background, the comparison sample changes significantly. Up here, there are very few comparison stars. These are quite rare stars within the solar neighborhood. But down here, there are lots of F-type stars. And that means if you actually compute the ratio of magnetic stars to non-magnetic stars within a mass bin, it changes quite a lot. So this is from the same paper. This is the fractional incidence. So magnetic stars divided by non-magnetic stars as a function of mass from about 3.8 down to 1.4 solar masses. I'll point out that this is a logarithmic scale here. So 10%, you'll notice that this distribution rises to 10% around 3 solar masses, and it's actually maintained there through all of the other A-type stars, through the B-type stars, and through the O-type stars. This is the canonical incidence of magnetic stars amongst stars with radiative envelopes. But pretty obviously, fossil fields are depleted in the coolest mass bins of this sample. So they start to disappear at the convective transition, which isn't so surprising because we know that there's going to be a transition from fossil fields to dynamo type fields. And so the purpose of this project is to understand and study what's happening to these fields as we approach the convective boundary. So from a physical perspective, we can build a lot of intuition by looking at a sunspot. So what I'm going to do here is define a criticality constant C, which is going to be the magnetic pressure or energy density to the convective pressure or energy density. And so you can think about this as like the dynamic pressure of convection fighting against the static pressure of the magnetic field. And in a sunspot, in the central region where convection is almost completely suppressed, that's where this value is much larger than 1. The magnetic field completely dominates, tells convection what to do, and hence the convective energy transport is almost arrested. We see a dark region that's quite cool. And then as we move outward into the penumbra, that value decreases to close to 1. So the magnetic field and convection are basically at odds with one another. And then as we move out into the quiet photosphere, this value decreases to less than 1 because the magnetic field is quite weak and convection again dominates. And so we're working with a model that was first produced by German and Cantiello in 2020. In this model, surface magnetic fields are hypothesized to be erased or processed by convection near the surface of the star. So convection is sufficiently strong to take weak magnetic fields and thermalize them to cause them to reconnect and disappear. But of course, if a magnetic field is strong enough, then the criticality factor becomes large, and it's possible for the magnetic field to resist that effect. So in this particular model, we calculate a critical field strength or a shutoff field strength that's necessary for convection to win over the magnetic field. Now, when they developed this model, they were actually thinking about hotter stars. But the basic picture was this. So here's the surface of the star, here's the convection zone. This is a loop of fossil magnetic field. And once we implant that fossil magnetic field, if it's sufficiently weak, then it starts to be modified by the presence of convection. Eventually, reconnection takes place. This part of the field is thermalized, it disappears above the surface, and then can reside below the convection zone. So like I said, they developed this model in the context of hotter stars to try and explain, for example, the magnetic desert. That's not our purpose here. We're going to co-opt this model in order to understand how the growing hydrogen convection zone at the convective boundary causes magnetic fields to be modified. So let's come back to our Kippenhahn diagram, and we're going to have a look at this upper left-hand region, the part that's really interesting to us, and we're going to think about it in that context. So around here, near 8,000 Kelvin, we have relatively weak superficial convection. That means the critical field that's required to suppress convection is pretty low, right? I don't need a very big magnetic field to turn that convection off. And so that means that at these temperatures, all of the magnetic fields that I can think of, weak magnetic fields and strong magnetic fields, should be pretty good at stopping convection, except for the weakest ones. On the other hand, and that's kind of like in the center of a sunspot, right? Most of the magnetic fields that we can imagine are going to be sufficiently strong that they're able to suppress this weak convection that's taking place. On the other hand, as we move to cooler temperatures, say around 6,500 Kelvin, the critical field is quite large. I need a big magnetic field in order to stop that convection from taking place because it goes down deep in the star. So that's a little bit like this region of the sun, right? Where convection is quite strong. It's only if I have quite a strong magnetic field that that's going to be possible. So we've modified the German Cantiello model. This is actually work with my thesis student, Todd Blanchette, to create a series of models that describe the shutoff field as a function of position on the HR diagram. So this is a logarithmic scale. So this is 1 kilogauss, and this is 100,000 kilogauss. On the HR diagram, you can see evolutionary tracks for the main sequence from 1.8 down to 1.2 solar masses. The color scheme corresponds to the shutoff field, and the blue dots correspond to a sample of cool magnetic AP stars that we've extracted beginning with the Untitled Chapter survey document from 2006. Refined using more recent work using TESS and Kepler data, and extracted the coolest 25 stars from that sample. And these are where they lie. So you can see there are lots of stars that should have magnetic fields that lie in this region. We know that these are magnetic stars because they're all rapidly oscillating AP stars. Rapidly oscillating AP stars have magnetoacoustic waves, hence they need to have magnetic fields. But the reality is that for most of these stars, we don't have direct magnetic field measurements. Some we do. So these 3 stars here are particularly interesting because we have magnetic observations of them. And those magnetic observations correspond to magnetic fields of 2 or 3 kilogauss. Right, so that would place them down here on this scale. But this is where they reside on the diagram. Right, so the model is telling us in order to arrest convection and for these magnetic fields to survive the convective process, they would need to be 100,000 Gauss, and yet their strengths are only about 3 kilogauss. So clearly there's a problem with the model. So let me tell you what the model is assuming. So the model is assuming that we have a magnetic field, and it extends through the entire hydrogen convection zone, through 30% of the star's envelope. Okay? So that's a lot of work for a magnetic field to do. Okay? So it's pretty clear that this particular assumption is already falsified. But what about assumptions like, a magnetic field that extends down to, say, 10% of the star's radius, or 2%, or 1% star's radius? So Todd carried out calculations for different, in his case, optical depths, where the magnetic field terminates. And he was able to show that for magnetic fields that only extend slightly deep into the atmosphere, say down to an optical depth of 100, it's quite possible for reasonable field strengths to be able to shut off convection and retain the fossil magnetic field. But the problem is, as I mentioned, we only have magnetic observations for a small number of those stars. And in order to perform a quantitative comparison between the model and the observations, we need those data. So in the meantime, my new honor student, Todd Beaudoin, has been obtaining new observations of the stars on that diagram. So here's one example. You can see the magnetically split line and the circular polarization here. Here's another example, stronger magnetic field, slightly more splitting, again, circular polarization. And so his job is to begin to accumulate new magnetic measurements of these objects so that we can perform a direct comparison between stars and the real magnetic fields and the predictions of the model on the HR diagram. Meantime, I've been trying to expand the number of magnetic stars that we can place on the diagram. And that was a topic of our conversation today. And the reason is because to do this properly, I need to be able to construct distributions, right? So to illustrate that, here's the distribution that comes from James Sikora's work of magnetic field strengths, right here, for stars that have temperatures around 10 or 12,000 Kelvin. And you can see it's an approximately log normal distribution like we were talking about earlier. And so what I'm curious to see is that if we take this distribution, which I kind of just pretended corresponds to maybe a temperature of 8,500 Kelvin, and I start looking at the distribution of magnetic field strengths for lower temperatures, what happens? And here's what the model predicts. As I go down in temperature, I should have a distribution that becomes truncated. The weaker magnetic fields should become less than the shutoff field value. Convection should begin to thermalize them and they should disappear. And so as we move down in effective temperature, the prediction of the model is that as we get close to the convective boundary, the only magnetic fields that should still be present are those that are much stronger than the mean magnetic field of stars across the HR diagram. So that's what we're aiming to do. We're not there yet, but that's what we're going for. To do that, I think we need quite a bit bigger sample than the 25 stars we have so far. Okay, so that brings me to my summary. So I've tried to express the fact that this convective boundary is a really special place on the HR diagram. Eugene and I went down to Corbett Park on Saturday and Sunday. It was very clear to us that watering holes were very important places in Corbett Park. If you wanted to see wildlife, this is kind of like an astrophysical watering hole. There's a whole lot of stuff going on there. Okay. And so I think it behooves us to try and understand not only the magnetic properties of stars, but as we were discussing earlier today, the activity properties of stars as they cross that boundary, in order to understand how this transition from stars like the sun to stars that are more like HD 24712 that we saw with the chemical abundance distributions actually occurs. So I tried to express that these coolest AP stars, as we move toward the convective boundary, are really interesting objects for probing that physics. They have strong magnetic fields. The chemical peculiarities are very intense and rely on the stability of their atmospheres, right? If the atmosphere begins to convect, then all of that gets mixed up and it goes away. And then some, we have these non-radial pulsations that also make them very interesting objects from an astroseismological perspective. And then in the final part of the talk, I talked about this new model of convective processing of fossil fields by the hydrogen convection zone that we're developing, and the hypothesis that this distribution of field strengths should shift towards stronger fields as we look at stars that are cooler and cooler approaching that boundary. So it would be my pleasure to come back in a couple of years' time with a sample of 150 stars that we'd observed, all of which have magnetic measurements, to show you the confrontation between this model and those observations, and ultimately to derive some sound conclusions. I think right now we're still at the experimental stage, but it's certainly been some good work from my students. So with that, thanks very much for your attention, and I'm happy to take any questions. I even gave you some potential questions to ask. Please.
This magnetic field decay in terms of the typical terms for decay. So these are like observable on time scales of years, or we cannot observe it. There's a decay in magnetic field.
Sorry, is your question, can we observe the decay, or do we observe the decay? Yeah. So the answer is no. And I think that's reasonable given the predictive theoretical decay time. So one of the ways that we can constrain the stability of these magnetic fields is to observe them over many rotations. So you may know that in the sun, the time scale for evolution of its magnetic field is a few times its rotation period. So if you look at an active region, after about 3 rotations, that active region will have either disappeared or significantly evolved. So we can observe stars with fossil fields for hundreds or thousands of rotations, and we observe no change. It's like clockwork. The magnetic field looks the same every time. Nevertheless, we can also look at stars that are, say, near the beginning of the main sequence and near the end of the main sequence and compare their magnetic properties. And there are differences. So what that tells us is that there are still evolutionary factors that can change fossil magnetic fields in stars over and above the very slow ohmic diffusion. So for example, as a star expands on the main sequence, it takes its magnetic field with it. But because magnetic flux is conserved, the magnetic field becomes weaker. And so the answer is they're stable, but there are other factors. I've really simplified things here. Please.
So these fossil magnetic fields are oblique with respect to the rotation of the. So is there any reason for that? Even the magnetars have oblique and they have no magnetically active system. It's like the fossil fuels are still there in neutron stars as well. And they are obliques. So since from the beginning they are oblique.
It's a really good question. So I don't have the figure with me, but there was a paper by Eveline Alician, who shows a figure of a hypothetical evolution of the magnetic field of the star as it evolves through the pre-main sequence. And in that picture, they show the star evolving down its Hayashi track and up the birth line with a dynamo-generated magnetic field. As it begins to heat up and its envelope becomes radiative, that dynamo stops. The magnetic field freezes out and becomes a fossil aligned with the rotation axis because it was a dynamo to begin with. And then as the star continues to evolve, circulation currents inside the star drive the obliquity. There were a number of papers back in the 1990s by David Moss that implemented a theoretical model that had the same ideas behind it. I don't know that there's really a lot of evidence that lets us say what the mechanism that produces that obliquity is. But I think you're absolutely right to note the similarity between the magnetic fields of these stars and those of neutron stars and those of magnetic white dwarfs.
What happened with the binarity? If we have a case with both stars are binary, as in case of the massive star, both stars are magnetic field.
We do. We have one.
Only one case, right? That is only one case. Since it has a wind as well.
I'm sorry?
It has a wind because.
Yeah, so these are two B-type stars.
It's correct. It's not exactly correct.
So
It depends on the scale.
So I'll clarify. There's one binary that is sufficiently close that the two stars are tidally interacting, both stars have magnetic fields. And it is unique and it is extremely interesting. The orbit of the system is slightly eccentric. It has an eccentricity of 30%. And so the stars are, roughly this far apart at apastron, and this is to scale, right? The stars are this big. And then at periastron, they're about this far apart. And so as they go through, the stars are forced to be tidally distorted. And we can measure that in the test light curve. We can see the light of the star heartbeat as they go past one another at periastron. We can see flashes of radio emission. This is PhD thesis work by Ian Bishwash, who studied at Pune before coming to Canada. As these stars pass one another and their magnetospheres interact.
Close to the peristron.
Pardon me?
Close to the peristron.
Exactly.
You see the plus.
Yeah, exactly. So yeah, there are a whole bunch of really interesting dynamical and energetic phenomena that take place in these systems.
But magnetic field is a thermal or non?
The magnetic field,
Sorry.
oh, the emission?
Sorry. Radio emission is a thermal or non?
Yeah, so it appears to be non-thermal. It appears to be ECME.
Second question is that Doppler tomography showed that the surface spots, why they are the regions are concentrated where we are in the chemical peculiarities.
Yeah,
Why the concentration is there?
right. So I mean, you're making kind of an interesting observation that puzzles people today. And that still isn't, as I said, well explained by theoretical models. And that is that, you can see these spots have relatively simple geometric distributions, right? Like this is a circle, for heaven's sake. And yet this circle isn't at the same spot as the negative magnetic pole of the star, right? It's slightly offset. This spot here doesn't appear to be associated with any element of the magnetic field. And so what is it specifically? So what the underlying physics is, the interaction of the field with the diffusion process that generates these lateral non-uniformities in chemical abundance isn't really well understood. Yeah, it's a great observation.
Yeah, in line with this question, so does this overdense region remain constant with time or change with time also?
So in almost every star, if you obtain maps like this 10 years apart, there's no difference. And that experiment has been carried out for a small number of stars because making maps like this, as you saw here, is observationally very expensive. I need a lot of observations. However, one of my master's students recently discovered a star with an extremely weak magnetic field. It's not a cool star. It's about 9,000 Kelvin. And this star has a 30 Gauss magnetic field. And that magnetic field seems to be sufficiently weak that differential rotation can still occur. And when we look at its spots, they seem to be being shorn with time. They seem to be changing with time. So again, that's another very interesting transition region between magnetic fields that are so weak that the atmosphere is able to sneak through the fingers of the magnetic field.
The point is that you have given the circular symmetry for the spots region.
I mean, shape of the spots are done.
Circular symmetry.
Circular, right?
Is it your input to with the circular symmetry?
No. So this is an ill-posed problem with freedom for the abundance on the surface of the star to acquire any value. So this is from 2018. So this is actually using a star that's divided up into a grid of about 5,000 different elements. And each of those elements can have its own abundance.
What is the grid size?
I'm sorry?
What is the grid size? Grid size. Grids. You said the.
Oh, the grid size. In this example, I don't really know. It's not the way we do it nowadays. Now we actually use a spherical harmonic decomposition to describe the surface. So the grid size is it's like 5,000 elements over the surface. And of course, we don't have 5,000 data to constrain the distribution. So there is an imposed relationship between different points on the star. We have a smoothness criterion that tries to limit either variations from pixel to pixel or the total amount of entropy or information in the map. But there have been many numerical experiments that have been carried out on this sort of work. We understand the systematics. Like, for example, in this particular star, if you think about this star rotating, there's part of the star that we never see, right? And the regions that are close to that, we get very little constraint on the structure. But the parts of the star that we do see frequently, they provide us with a lot of information. So the reality is that, so two things. The reality is that the structures are in their large scale, they're robustly constructed. But the second is that when you look at them on a spherical projection like this, everything tends to look a little bit spherical. If you look at them on a rectangular projection, then you get a better idea of how asymmetric they are. So another good question.
Yeah, about the diffusion model, is it very unique or you parameterize it in these investigations?
The theoretical diffusion model?
Yes, yeah, in these cases. Yeah.
Oh, I mean, there are a bunch of different evolutions of the diffusion model. The basic physics is pretty straightforward, right? You have an atom in a particular excitation and ionization state. A photon arrives with a particular energy. It transfers a certain amount of momentum. And then you compare the gravitational acceleration with the radiative acceleration. If this one's bigger, it goes up. And it continues to do that until it arrives in a cooler region of the atmosphere where it changes excitation or ionization and then stops there.
Okay. And the magnetic field, you assume a constant value, or it is like?
Again, it depends on the model. Yeah, good question.
Any more questions?
Gregg, I have one question.
Santosh.
So, about you have this non-magnetic and magnetic stars, right? Spot, if we take the spot topology. So how their high magnetic, intense magnetic field and non-magnetic field affects this spot topologies? I mean, how it is affecting me in case of the sun. So, the intense magnetic is local, a few kilovolts, but in some cases in these stars are 50 kilovolts or so.
Right, okay. So,
So how their this topology is going to affect?
yeah.
Are they still the circular shape or?
So largely speaking, stars without magnetic fields don't have spots. They don't have non-uniformities. However, they can still have peculiar abundances of chemical elements, but they tend to be far less intense than the magnetic stars. Why? The magnetic field serves to stabilize the atmosphere and to make the diffusion process more efficient. There are a small number of stars in binary systems called Mercury manganese stars that seem to show abundant structures that have shapes a little bit like this. And those abundant structures, like the star I was talking about earlier, change with time. And so they appear not to be related to a magnetic field because they're non-magnetic stars, but rather to, well, I don't know, weather in the star's atmosphere probably related to its presence near a close companion.
Any more questions? Okay, let's
Yeah,
thank, yeah, yes, please.
Sorry.
Yeah, please.
We consider the angle of inclination with the rotation of the field in the modeling. Otherwise,
Yes,
you can't see the
absolutely.
deep, you can't see the depth deep in the line profile.
Yeah, so input data into the model, typically the projected rotational velocity, so that you can fit the line profile.
Right.
Related to that is the inclination angle, I. The atmospheric parameters of the star, yeah.
Exactly similar to that.
Yeah. And inferring I is pretty easy for these stars because you can determine a radius reasonably precisely. And then once you have V sine I, you can infer I because you know the rotation period. And then, of course, you can run different models around that initial value to find which one optimizes the fit to the profile.
That is restricted to your angle of inclination. It is a low and higher, you can't get the fit in the line profile.
Yeah, that's right. So if you have an inclination axis pointing straight towards you, you actually see no rotational broadening because the star is doing this. And then when you get here, you get maximum rotational broadening, but then you can't distinguish the two things. So the optimal situation is an intermediate value. Yeah, there's no such thing as a free lunch, right? There's always a drawback to any geometry.
Okay, if no questions, let's thanks again the speaker.
Thank you. If this was working at all. No. I didn't see the right one.
Okay, really how does it?